Hello everyone, welcome back to the How series. We are beginning session 6, which starts module 3. Module 3, performance optimization, is a demonstration of all of the optimization techniques that we are planning to cover in the rest of the week. For the case study, I will use an n-body simulation, and you will see how it evolves in a minute. Just a second while I fix my pen. Okay, ready. So, if you have just joined us, make sure that you check out the course web page. On that page, you can download the slides, code, watch video recordings, and ask questions in the chat. The chat is at the very bottom of the page, and you can type as I speak. We will take care of your questions as they come in. For questions that you want to ask offline, or for questions that require an extended answer, please feel free to use our forums. This is a hands-on workshop. I will be demonstrating what I teach today on the Colfax cluster equipped with Xeon processors, Xeon Phi coprocessors and processors, and you have access to this cluster too. Once you register for the webinars, you should receive an invitation from cluster@colfaxresearch.com. If you have not received it within an hour or so, please check the spam folder. If it's not there, send us an email. And we are going to talk about performance optimization. And a reminder of the key message of this course. Even though we will be testing our code on a variety of platforms, multi-core general-purpose CPUs, and specialized many-core processors and coprocessors, the idea is to learn a set of practices that allows you to design a single code that will be efficient on all of these platforms, portable across them, and also compatible with future generations of Intel platforms. To achieve these conflicting goals, optimization and portability, we will use modern code practices. With these practices, we are going to make our code cognizant of the fundamental building blocks of our architecture: multiple cores, vector instruction support, high bandwidth memory, and high performance fabrics. But we will not make it tied to a particular architecture, because we will rely on standards for multi-threading, vectorization, and offload. Last week, we covered OpenMP, the Open Multiprocessing Framework, that historically was designed for multi-threading, but in its most recent versions, it also supports vectorization and directives for offload. And another reminder of something I covered earlier in our discussion of performance optimization. We are focusing on taking a particular numerical algorithm and implementing it as close as possible to the underlying computer architecture. So we do not have the ability to go into domain-specific details, such as finding analytical problems, approximating your real-world problem with an analytical model. We are not going to talk about numerical methods or about discretizing the analytical model. This is a subject of computer simulation and algorithms. We are operating at this last level. A particular numerical algorithm, how do we implement it close to hardware? Sometimes you can find better opportunities for optimization up there in the pyramid. And today will be a perfect example of that. We will use a primitive algorithm that is easy to optimize. And I will also make references to more complex algorithms that are more difficult to optimize, but at the same time to implement close to hardware. But at the same time, they perform fewer operations, so for large enough problems, they eventually win. The goal of today's demonstration is to give you a sample of programming and optimization techniques that we have for scalar tuning, vectorization, threading, and memory access. That's node-level optimization, and optimization of communication with the help of MPI. The idea is that all of the optimization techniques we structure into these 5 areas. And for each of these areas, we have targeted exercises. And we're going to have lecture sessions discussing scalar tuning and optimization of vectorization, a session discussing the optimization of multithreading and the interface between multithreading and memory. And we will talk about specifically optimizing access to memory and caches. And today I'm going to give you a sample of many of these techniques and show you how they work together, and most importantly, how you can understand where to go next. Importantly, I will be targeting all 3 platforms that we have in the cluster: Xeon, Xeon Phi coprocessor, and bootable Xeon Phi. This picture shows a Xeon Phi processor. To remind you the fundamental building blocks, there's multiple cores in it. Cores can run independent programs. In our case, they will run the same program on different data sets. Inside the cores, you have vector processing units that can apply a single stream of instructions to multiple data elements at once. And when cores communicate to memory, they automatically get their data cached in the level 1 and the level 2 cache. And if we take care of data reuse, we will take advantage of this hierarchical cache structure. These are the fundamental building blocks that we are going to target. Okay, let's move on to the technical subject today, the n-body simulation. I think that before I explain the mathematics, it makes sense to show a picture, or better yet, to show a video. So this is a video clip of one of our older presentations. We recorded it for Supercomputing 2012, when Xeon Phi was first announced. And this is a simulation of a collision between 2 galaxies. It is a toy model and not very meaningful initial conditions, but you can see what's happening. Every particle exerts a gravitational pull on every other particle, and we are simulating how these particles move in response to the gravitational forces produced by these same particles. First, you saw a slow animation that was running on a Xeon processor, next on a Xeon Phi coprocessor, and now on 2 Xeon Phi coprocessors. And the key message of this demo is not the particular performance, but rather that we are using the same exact code on the Xeon and on the Xeon Phi. The mathematics of what we're doing is this. We have point particles, many of them, well, n particles. If we had 2 particles, we could solve this problem analytically, but for 3 and more, there's no practical analytical solution. To solve how particles interact with each other and how they move in response to these interactions, we use Newton's law of universal gravitation. If you just take 2 particles, they pull each other, and the force of this pull is the product of their masses divided by the square of the distance between the particles and multiplied by the direction vector. Well, to get the direction vector, we actually used the distance vector in numerator, and instead of a square, we used a cube in denominator. So suppose this is the particle of which I want to compute motion. I want to take this partner and compute the force with which this partner pulls this particle. Then I take another partner and I compute that force. And then I add all these forces as vectors. Eventually I get the force, the net force on this particle, and I will use it to solve the equations of motion. It is going to be computationally intensive. The amount of data that we have is O of n. what is the amount of computation that we have to do? N squared. Why? Well, that's because the sum is over all partner particles, so it has n minus 1 terms. For each term, I have to do this math, and then this gives me the left-hand side. And there's as many left-hand sides as there are particles, so n. So I will have to compute n times n minus 1 particle-particle interactions, and for each interaction, I will have to take the coordinates of the particles, take the difference, square, add, square root, cube, all of that. This problem is definitely applicable to astrophysics, like I showed you the image of the video of a simulation of colliding galaxies. This is actually a process occurring in nature. As proof, here's a beautiful picture from the Hubble Space Telescope. These are two colliding galaxies. When they collide, there's so much empty space that stars don't actually collide with each other. What's colliding is gas and particles moving in response to the self-generated gravity forces. In astrophysics, n-body problems are also found in simulations of planetary systems, galaxies, and cosmological structures. The biggest structures of dark matter and gas in the universe. The same exact mathematics is actually applicable to a different physics law called Coulomb's law, and it is applicable to electrostatic systems. So when you're modeling molecules and crystals, you will be using the same mathematics. What we are using, the n-squared algorithm, is actually a toy model. It is the simplest implementation, the simplest discretization of the real-world problem. There are more advanced algorithms that use approximations, and they reduce the complexity from n squared to n log n. If you're dealing, like in astrophysics, with billions up to hundreds of billions of particles, then n squared is a huge number, and n log n is a tremendous, gives you tremendous savings in computational time. But this is an approximation. It could be a pretty good approximation. At the same time, at the core of this approximation is the toy algorithm that we are going to implement. Okay, let's begin implementing it, and we are going to do this on the cluster. I have 2 sessions already open, and for the exercise, we will go to House Series Labs, Chapter 4, Lab 401. What are we doing here? We have n-body.cc, and this is our source code. Well, how is it structured? From top to bottom, I am declaring a data type called particle type. As you can see, it is a structure containing the coordinates of the particle and also its velocity component. Makes sense. Looks like it makes sense. I have n particles. I have to store their data somewhere. Why not store it in a convenient object representing a single particle, and then create an array of such structures? Even though it looks logical, and it actually seems like good programming style, because it is object-oriented programming, it is not optimal in terms of performance, and we will see why later. I want to explain why there is no masses. My assumption is that all masses are equal to each other and equal to 1. 1 because this is how I choose the system of units, so that all masses are 1. Very convenient for computing. Here is the key function, move particles. Its goal is to compute all forces using n squared operations, and then move particles in response to these forces. It is built around two nested loops. One loop iterates over particles that experience force, particle I. The other loop iterates over particles that exert force on particle I. So the outer loop iterates over different left-hand sides. This is the I loop. The inner loop iterates over the terms in this sum. What has to happen inside is this exact calculation. Force Ij is equal to 1 over the square root of Ri minus Rj. I'm sorry, oh, not square root, but modulo absolute value cubed times Ri minus Rj. I think something like this. And this is what I'm doing. Ri minus Rj, I have to compute it component by component. So I compute dx, delta y, delta z, and then I compute dr squared. So dr squared is actually Ri minus, I'm sorry, it is xi minus xj squared plus yi minus yj squared plus same for z, and the square root of that is Ri minus Rj first power. And so because I need it in denominator denominator cubed, I use the power function. And then I accumulate the force in those temporary variables. This is the force on particle I. Once I have the force on particle I use this force to solve the equations of motion using first order Euler method. And then once I know the updated velocities, I solve for coordinates using the same method. Just a couple of comments about this algorithm. One comment is people who know physics know Newton's third law, and they know if between these particles the force of interaction, if this particle pulls on that particle with force F, then the reaction force is negative F. So sometimes people think, well, can't we cut the number of calculations by 2 by taking advantage of Newton's third law, meaning force Ij is equal to negative force Ji. And in principle, we can. This would require that this loop goes from J to I, and then we save these forces somewhere and retrieve them. You can try to do it yourself. If you're successful, you will find that it is a bad idea in terms of performance, because you have many memory lookups and you have a catastrophic situation with vectorization. So even though this is a better algorithm, it makes fewer operations, you will see that the implementation of this algorithm is not working well on Intel architecture. So we will discard this option from the beginning, but you're welcome to try it. Another comment is this, the softening. This is used for two reasons. One reason is to elegantly handle the situation I equal to J. You see, when I equal to J, you're computing the force with which a particle pulls itself. Physically, this force should be 0. But mathematically, if we compute the force of interaction with yourself, then the distance will be 0, and you will have a 0 in denominator. We don't want that. So this is why you use the softening. You can check what's happening. If we use if I is equal to J, then all of these are 0. This is a small number. This is a small number. And then you have 0 divided by a small number, which is numerically 0. That's good. The second reason for the softening is that when particles approach each other too small, and delta x plus delta y plus delta z are all small, it will prevent the particle solver from blowing up, and so it improves stability. This is a little trick that is used universally in n-body simulations. Another comment that I want to make is regarding the solver. The solver that we are using is first order Euler method. This is the most primitive solver that you can imagine. Basically, it solves f df dx equals df dx equals y of x I'm sorry, equals y of x using the approximation fi equal to f delta t. Okay, using the approximation, f of x plus delta x is approximately equal to f of x plus y of x delta x. This method is known to be unstable for large delta x, and it is only first order accurate. Neither are good characteristics of solvers for differential equations. My claim is that it doesn't matter for our purposes. Our goal here is to optimize not accuracy, but performance. And with respect to performance, most of the calculation is occurring here in this loop, simply because this loop is executed, well, n times. Well, let me say it differently. Most of the calculation is here in the body of this loop, because it is executed n squared times. This solver is executed n times. So even if we went for a more advanced solver, such as the second-order Runge-Kutta method, we would still have a negligible amount of time in the solver. So the nature of the solver is irrelevant to the optimization of performance. And we are using a simple solver just to avoid distraction. It is not relevant for our purposes. And the same applies to the solver for coordinates. Okay, in the body of the function, you can see that we can specify how many particles we want to use in the first command line argument. We create an array of structures containing all particles. Because we need to initialize this array with something, we use a random number generator here, and then when we perform the benchmark, that's what we do. We make several time steps. That movie that you saw was an animation of multiple time steps. So each time step is going to be one iteration, and we are going to time it. We're using the OpenMP timer for timing, and then we convert time in seconds to performance in units of gigaflops per second. The assumption is that every particle-particle interaction is 20 floating point operations. And we are making n squared particle-particle interactions in delta t time. This is delta t. So we can convert time to floating point operations per second. 20 is an interesting number. It is just a convention in this field. Every paper on n-body simulation that I've seen uses 20 to estimate performance. You can try to count how many floating point operations are here, and it's not clear. Maybe this is 1, 2, 3, then 4, 5, 6, 7, 8, 9. I don't know, is this 1, 2 operations? 10, 11, 12, 13, 14, 15, well, something like 20, close enough. So I will stick with 20, just like all other authors, so you can compare our results to what other people are getting in the literature. And basically that's our simulation. Full disclaimer, this is not an optimal code, and this is the whole idea. We are going to see what it takes to optimize it. So let's compile and run it. When I type make, as usual, you will see 3 compilation attempts. One makes a CPU executable because it gets compiled with XAVX. This is for the Ivy Bridge architecture. There's also Knight's Corner executable because it gets compiled with MMIC. And there's a Knight's Landing architecture because it gets compiled with XMikeAVX512. So this is KNC, this is KNL. But we use the same exact code for all platforms. If we want to run it, thankfully we have the targets Q CPU and make Q KNC and make Q KNL. Well, here it is submitted. While it is processing, I'm going to create a log. So original code. So Xeon, Ivy Bridge, Xeon Phi, Knight's Corner, and Xeon Phi, Knight's Landing. We are doing a single precision simulation. So theoretical peak performance is a relevant metric. The estimated theoretical peak performance for the Xeon model is in single precision 500 gigaflops per second. For KNC it is 2400 gigaflops per second. And for the Knight's Landing, I think it is a 4,000 gigaflops per second. Actually, for Xeon Phi, we can probably do the estimate. So 64 cores times 1.1 gigahertz. One clock cycle is 16 operations, and if you do fuse, multiply, add, it's 2 instructions per cycle. So we can do the math. 64 times 1.1 times 16 times 2 is... did I do this right? I think I didn't do this right. Fuse, multiply, add is 2. Oh, because we have another 2. We have 4500. We have 2 vector processing units, 2 instructions per cycle, and fuse, multiply, add gives you 2 operations as 1 instruction. Okay, so here's what we expect. What did we actually get? Is it done? So on the CPU, this is how it's organized. It took 1 second, and then this second is converted to gigaflops per second, and we get 5.3 gigaflops per second. So I'm going to type original, and 5.3. 5.3 is not a lot compared to the theoretical peak of 500. And KNC gives me 0.8 gigaflops per second. Well, 0.8 is completely miserable. How about KNL? KNL. We get 3.6, so better than the Knight's Corner, but worse than Ivy Bridge. Let's see why we are not getting anything close to the theoretical peak performance. And I think if you attended session 4, it should be completely apparent to you. The lowest hanging fruit is the threading. This code knows nothing about multi-threading, and it is running on processors that have respectively 24 cores, 61 cores, and 64 cores. All of these cores require multiple instruction streams, and we are just running one. So we need to parallelize it. And we know that OpenMP is very good at parallelizing loops. So which loops do we have? Well, inside move particles we have the loop over I, the loop over J, and the function move particles itself is contained inside of a loop over time steps. So which loop can we parallelize? Steps, I, or J? Think about it for a minute. Yeah, think about it for a minute and think about the reason for choosing one or the other. Obviously, we want to, you can type your suggestions in the chat, by the way. Feel free to comment what I'm doing in the chat. So, obviously we want to expose as much parallelism as possible, so we want to go as far out as possible. Can we parallelize the loop over steps? Well, I don't think so, because the idea of steps is to take particle coordinates at time t and evolve them to particle coordinates at time t plus delta t. This is one step. The other step is going to take these coordinates and evolve them to x of t plus 2 delta t. And in order to do that, I already have to know the answer of this step. So I cannot run these steps in parallel. What can I do? How do I choose between I and J? Let's try both, see what works best, and then try to explain it. The loop in J seems to be straightforward to parallelize. We've seen this exact parallel pattern in the integration routine. Pragma OMP parallel is an OpenMP directive to create threads. Well, each thread is going to run whatever is inside the pragma. So if we want to distribute different values of J to different threads, then we have to put 4. And we have to look out for data races. There's no data races here because all the data is written into temporary variables. But this is a data race. This is a data race because F is shared across threads. But thankfully, all that we do to F is we increment it. And we saw in session number 4 how we can work around this using the built-in reduction clause. So we are going to declare that fx, fy, and fz are special variables. We are going to have concurrent access from multiple threads to these variables, but all we are going to do is incrementing them. OpenMP knows how to do some transformations behind the scenes so that you actually increment thread private variables and then you do reduction at the end. But this is all we should need to do. So recompiling and resubmitting, and let's see what performance comes out. So we parallelized the J loop. And what did we get? We got 33.7. Well, let's do two significant figures. Let's do 33.7 gigaflops per second. Well, this is much better than before. Not great, but better than before. On Knight's Corner, we are getting 7.0. Again, much better than before, but still not great. And Xeon Phi. Xeon Phi gives us 13. This is a speed up, but Xeon Phi is still doing poorly compared to the Xeon, and the speedup is not great. It's not even equal to the number of cores. We would expect a speedup by a factor of 24 on the Xeon, but it's not there. The reason for this, there are two reasons for that. One reason is that when we set up parallelism in the J loop, this loop itself is inside the I loop. So a total of n times, and in our case n is 16,000. A total of 16,000 times I will have to start and stop threads, I will have to start and stop scheduling, and this is a significant overhead. And the second reason is that there's not much parallelism here. We have 16,000 particles, but you can actually look in the optimization report. We will do it in a second. This loop is already vectorized. So instead of 16,000 particles, we have at best 1,000 vector iterations, and we are distributing them across 256 threads. And this is not enough to even get good load balancing on Knight's Landing. So let's try to parallelize the other loop, the loop in I. We are going to take it back, parallelize the loop in I, pragma OMP parallel 4, and let's look out for data races. This is no longer a data race because these variables are all private to every iteration. Correspondingly, they're private to every thread. So there is no data race because we don't have threads writing to the same memory location concurrently. This is suspicious. We are writing to memory, but because we are parallelizing the loop in I, different values of I go to different threads. So we will not have different threads writing to the same memory location. So we are safe. And here, the parallel loop actually ends, and we have this loop to process. Well, we parallelized that loop. Why not parallelize this one too? We cannot fuse these loops because we would get incorrect results, but we can certainly parallelize both to get a speed up. Recompiling, rerunning. Let's see what comes out. Log. So what we did now is parallel I loop. Let's see. Everything is done. Well, this is much better. We are getting on average 144, but you can see that the sustained performance is more like 149. This is some warm-up, and we are going to record 149 megaflops per second, 3 significant figures. And then Knight's Corner gives us 35. This is 119. Not bad for just moving one directive to a different line. Of course, this is not a difficult code to parallelize, but you can see that the choice of your parallel strategy can have a huge effect on performance. To simplify this in the future, let me figure out a command to just get this performance. Does it look right? Looks right. So let's, I'm just listing the output files, and I'm just going to grep for average. Looks right. Okay, so the last 3 lines are going to be the last 3 performance values. It's a little difficult to figure out what's what. How do we act? Let's do that. Sorry for the delay, just trying to speed things up down the line. Is that better? A little long. Does that fit? Okay, perfect. Now the last 3 lines give us the performance values. Okay, so what next? Looks like we parallelized the code and we achieved a significant speedup. The speedup is actually good. If you do the math, this is roughly 24. This is roughly 140. We discussed yesterday that the expected speedup for Ivy Bridge is the number of cores. For Knight's Corner, it is at least twice the number of cores. And for Xeon Phi, the expected speedup is at least equal to the number of cores, usually more. This is approximately 100x. And there's 64 cores, so we're fine. Where do we go from here? Well, looking on our diagram, the optimization effort should probably contain these 5 areas of optimization: scalar tuning, vectorization, threading, memory access, and communication, if we're doing cluster computing. We addressed this component, and we have 3 more left in the node level optimization. So which one do we pick next? Often this is not a trivial answer, especially if you don't know where your code spends time. But because we do know where the code spends time, we have the ability to ask the compiler what we have to optimize next. The code spends most of the time in this loop because it gets executed n squared times. The body of this loop is executed n squared times. So our application is simple enough, and we can go and look in the optimization report. How about Knight's Landing optimization report? The loop is in line 20. And what does the compiler have to say? Well, it says it was vectorized. This loop was vectorized, which is good and really unsurprising because, well, if you can do this calculation for one value of j, you can do it for many values of j. And I explained how this is going to be vectorized back in session number 3. I showed this code snippet. You can look it up. But this is not enough information. And to get more information, we will need to edit the make file. In the make file, you can see that there's already qopt report. It requests the optimization report. I will just change this to qopt report equals 5. Equals 5 will increase the verbosity of the report, and it will give us more clues about how to proceed. Well, with this done, I can rebuild. And with the code rebuilt, I can go to the optimization report again. Line 20. Well, here's what the compiler has to say. This loop was inlined into the main function. Well, good for you, compiler. Then, non-unit strided load was generated. This is interesting, and this is a red flag for optimization. This is something that we need to address. I am going to do it later, though. Let's read the entire report. So vector length 16, good news. Vectorization overhead. Oh, this is large. This is close to 1. Then, floating point up converts and down converts. Well, this is completely nuts. We are trying to run a single precision code, but we are getting single precision to double precision, 2 conversions, and 1 conversion back. All of them are in line 30. Extremely suspicious. And then if I keep going, I also have hints about stranded loads, which actually is a mirror of that message. Estimated potential speedup is small, which is actually a mirror of this large overhead. It is small compared to 16, which is the vector width. There's divides, which is also a red flag. This is a heavy operation. And type converts. Well, the type converts really seem like they don't belong here. And they occur in line 30. So we are going to look at what we can do. So naturally, the compiler prodded us into the direction of scalar tuning with red flags in the optimization report. Okay, so let's do scalar tuning. Line 30. What's happening in line 30? In line 30, we have this power function, and we are raising dr squared to power 3/2. Well, it actually gives us dr to power 3. I don't know why it says 32. It should have been 3. This would be a better name. It doesn't matter for accuracy or performance, but better name would be 3. So why is this incurring type conversions? This is actually a multi-part problem. And let me explain. We are trying to do everything in single precision. Float is a 32-bit floating point representation. What's happening here is we're calling the power function. This is C++. So people, many people, come to expect function overload in C++. Meaning that when you change the arguments of the function, you call a different body of the function, and you expect that the C math library would be optimized for that. It is, but there's a couple of catches. So one catch is that the power function in the global namespace is not overloaded. It is only overloaded in namespace std. Okay, so in namespace std, the type of the arguments will determine the type of the function. Without it, what we were doing is we were calling a double precision function with single precision arguments. So by the rules of the C++ language, you have to promote the single precision value to double precision, then you have to do the power function of a double precision number, get a double precision result, and convert it back to single precision. Unnecessary math. Now, we should be getting overload, and we should get no type conversions. Okay, let's check that. Compile. Reread the optimization report. Line 20. Okay, non-demonstrated load. Wait a second. Number of up converts still 2 and down converts still 1. So what happened? Didn't I say that you have overload? Does anybody know? If you have ideas, post in the chat. So yes, this function is overloaded. It will change its implementation depending on the nature of the arguments. Our problem is with the arguments. This is a true single precision argument. But that is a problem. This is a literal constant. And there is a frequently ignored rule that literal constants in C and C++ are, by default, double precision numbers. If you have a decimal point, it's a double precision number. So this is actually a double precision number, a 64-bit value. So the compiler has to promote this to double precision, do the math in double precision, convert the result back. If we want these literal constants to be interpreted as single precision numbers, we have to use the suffix f. The suffix f declares them as 32-bit numbers. Well, let's see what that does. Recompile. I will actually submit it to the queue while I take a look at the optimization report. And what we have is non-unistride load, and yeah, no type converts. There are still divides, but this is a different story. We will address it in a second. Okay, so it's running. Did it finish? Looks like it did. And these are the latest performance values. So let me write them down. All we did is we removed unnecessary math, which was wasting resources on type conversions that we did not really intend. So power we replaced with std power, and we also replaced literal constants with the appropriate suffix so that we get overload working correctly. So now CPU gives us 200 gigaflops per second. Knight's Corner gives us 170, and Knight's Landing gives us 478. Well, not a bad performance boost from just scalar tuning, changing the nature of the operations that I'm running. This is a legitimate solution, and let me show you how to achieve the same result with a different method. If I was using C, then I wouldn't have namespace std. In C, my solution would be different. It is a frequently ignored fact that when power is the double precision function, there is actually its single precision counterpart, power f. And it achieves the same result as the previous case. Namely, it gets rid of type conversions, and the code just performs better. So our fix was in fact, yes, no type converts. Our fix was in fact this single letter. Just adding the letter F would make the code this letter F would make the code faster. Well, this is not optimization as much as it is a bug fix, but this is a common bug. Well, you can see that we get the same results within the rounding, within the fluctuations. Okay, so we did that. And coming back to the optimization report, we see divides. Divides is a red flag for optimization. The truth is that the division floating point operation is very heavy. In session 7 tomorrow, I'm going to show you a table listing the latencies and throughputs of various instructions, and division is one of the most long latency and low throughput instructions. Divisions in our code, of course, occur here. In some cases, it is possible to do what's known as strength reduction. Strength reduction is when you replace one expensive operation with some less expensive operations. This may change the accuracy of your code, but depending on whether the nature of your calculation allows it, it might result in a good performance boost. So what I'm going to do is get rid of divisions and replace them with multiplications by the reciprocal value. So I will call it 1 over dr, and I will compute it as 1 divided by the square root of dr squared. I'm not going to fall into the same trap as before. I'm going to use f on the literal constant, and I'm going to use square root f. And then what I need in the denominator is the cube of that. So const. Oh, I'm sorry. I think I'm running ahead of myself. What I'm going to do is this. I am going to compute this thing to power -3/2, and I will multiply. This is dr to power -3. And I have to multiply by this value rather than divide. Once again, it might change the accuracy, it might degrade accuracy, but it is a lot faster. If we are concerned with performance optimization, let's try what it does. Done. And the last three numbers are our optimized performance values. Let's see how much of a difference this makes. So log. What I did is I replaced divisions with multiplications, and this gave me 275, 202, and 602. So that's the operation that I performed, and I think it makes sense for this case. And something else that I'm going to demonstrate, a less trivial step that nevertheless makes sense, is the replacement of this power function with a square root. I don't think it will do anything, but let me do that, and then I will explain what this does. Oof. Excuse me for a minute. Okay, I think we're fine. Press the wrong key. So what I did is I replaced the power function with the reciprocal square root. And then cubed it. I think it will not change anything. The reason I'm doing this is just to be safe for possible compiler updates. The reciprocal square root function is actually implemented as one of the new functions in AVX 512 ER dataset supported by the Knights Landing processor. This function is highly optimized. It is a high throughput, low latency function, much more efficient function than the power function. Well, we were using the power function in a degenerate case. We were raising something to power 3/2, which is equivalent to taking a square root and then cubing it. The compiler might have performed this replacement automatically, but I am not 100% sure. So let's check. Yeah, it looks like I'm getting the same performance as before. So that was already done. But this is just another example. One last step that I'm going to make before we take a break is, now that we are dealing with scalar tuning, why not push it all the way through and also relax the floating point semantics and possibly request lower accuracy transcendentals. Basically do the math as fast as possible. I will include a new compiler argument, fp model fast equals 2. I will explain it tomorrow, but basically if you are going for the highest performance at the cost of the lowest accuracy, makes sense, for example, for some Monte Carlo calculations, use this argument. It uses the most aggressive optimizations for arithmetics that you can make. Recompiling, rerunning. And to tell the truth, it doesn't change anything. It doesn't change the results of this code at all, because all it does is excludes the handling of denormal numbers in transcendental functions. Denormal numbers fill the gap between 0 and float min, and their handling is optional, but these denormals are flushed to 0 in Knight's Corner anyway. They are still handled by software, which doesn't make sense. So fp model fast equals 2, just to push the scalar optimization to the limit. This is done. And our best performance values now are these. I'm not sure about this number. Let's rerun. I think we had a fluctuation. I know why this is happening. I'll just run again. I think it was a one-time fluctuation, and the most common performance is actually higher. Yes, that's better. Okay, so we are getting to 81 gigaflops per second. On KNC, 212 gigaflops per second. And on KNL, 654. Well, we touched on these two performance optimization areas, threading and scalar tuning. We have not touched even we have not even touched vectorization or memory access, but we are already operating orders of magnitude faster than what we started with. Let's take a 5-minute break. And after the break, we will go to vectorization, tuning, and memory traffic. Feel free to keep posting questions in the chat, and I am going to mute my microphone and resume in 5 minutes. Okay, so in the first half of today's session, we optimized, well, implemented multi-threading, and then optimized the scalar aspect of the code. Next, either vectorization or memory access. But where should we start? I think once again it's a good time to ask the compiler. Let's simply look inside of the optimization report, and we will look once again for the most important loop, which is always the innermost loop, the one in line 20. So line 20. As you can see, there's no more divides, so no more divisions, so I have no other scalar optimization opportunity, but I have more red flags. Non-unit strided load for variable particle of j with a stride of 6, and this happens in lines 26, 27, and 28. I also see very high normalization overhead and the estimated potential speedup much lower than 16. This tells me that I need to pay attention to vectorization. So what is non-unit strided load and why is it occurring in these three lines? What's happening in these three lines? These are the three lines that the compiler complains about or warns me about. And what happens here is the lookup of x, y, and z coordinates from the particle array. This loop is vectorized. When it gets vectorized, several values of j are glued together, and all scalar operations become vector operations. But before they become vector operations, as I explained in session 3, the code must load our data from memory into the contiguous vector register. Loading this is not a problem because it has the same value for different values of j. So this will become a vector in which all vector lanes contain the same value. But that is a different story. Here I have to produce a vector that contains particle 0.x, particle 1.x, particle 2.x, and so on. This will become my vector, 16 wide. But because we chose an array of structures, this is very inconvenient to load from memory. I actually have a diagram that explains what happens. And this diagram ignores velocity components, but you can certainly generalize it mentally. Our data that we're loading into the contiguous vector register is not contiguous in memory. I have to go with a stride to get to the next component. And because memory access works in units of cache lines, a cache line contains 64 bytes or 16 single precision numbers, I will effectively neglect 2/3 of the data that I load from memory. If only I could transform my code into something like this, a structure of arrays, or just plain arrays, I would be doing unit stride loads, and this will be much more efficient. Now, the bad news is that it is not always trivial. There is a library called the Intel SDLT called, I think it's SIMD Data Layout Template. What this library does is it allows you to keep the structure of your code, but behind the scenes to change your data containers so that you actually have an array of structures, a structure of arrays behind the scenes. But we are going to do it by hand just to see what exactly needs to be done, and also to see how non-trivial this might be. Instead of this type of structure, I will create plain arrays Well, just to simplify argument passing, I'm going to enclose these arrays into a structure. So by putting this asterisk, I'm making those pointers pointing to arrays, and I will call it particle set type. So this is my new data structure. I will have to change the code everywhere that I use particles. I will pass by reference such a structure. The whole idea was to move away from particle j.x and to get particle x of j. So this is the key transformation I'm doing. When I'm doing my vector calculations, I want to load from memory sequentially. And this is going to be a lot of typing. Thankfully, the code is not too long. And you can see that it is also prone to errors. But because I've done that in the past, I know that I can actually use some editing magic and do this quickly. Still a lot of work. The same is going to have to happen to velocity components, even though it's not important for vectorization here. We did change the data layout, so we have to reflect it everywhere. So this to that, this to that. Now in the main function, this no longer works. Instead, what I should do is to create particle set type. And this is a structure that contains arrays. So I will have to do particle .x new float and particles. Just to simplify my work down the line, let's change this to C-style allocation like this. I think this is correct. X, Y, and Z. All of these. And the same for velocity components. This will have to be changed. All right. Oh, I don't have to change anything here because I'm already passing the structure of arrays. Yeah, but this is not going to work. We are going to have to do free particle.x, y, and z. And the same for velocity. I hope I did everything right. And again, the key was to address the array first and the index next, and not the other way around. Seems to compile. Let's execute. And while it's running, I will prepare the log. So we did a conversion from an array of structures to a structure of arrays. The motivation for that was a message in the optimization report that said non-unit strided loads. Do we still have this message? The loop is in line 24 now. So what we have now is a remark about peeling and unaligned access, but we have unit stride loads, and this is good. So we are optimizing vectorization. Loop was already vectorized, but the loading was done in a very inefficient manner. We changed the data layout to optimize data loading. You can see that the estimated potential speedup is now much closer to 16. Okay, and we don't have any complaints about strided loads. We do have a new remark about peeling, but we will get to it in a minute. Let's see how performance fared. So, all done. Here are the last 3 performance measurements. You can see that, well, let me write them out first. The CPU gives us 386. KNC gives me 1174. And KNL gives me 2050. While this is absolutely tremendous, we did not change anything about the math of the code. What we changed is memory access. And this goes back to the warning that I gave you in session 3, that you can vectorize all day long, but it will not matter if you don't optimize memory access, because math is cheap, data access is expensive. This was a 50% performance increase. This was a 5x performance increase. And this was a 3x performance increase, just from changing the data layout. I think this is very significant, and we will keep the code as is, even though it took quite a bit of work to arrive at this solution. That's the key to this transformation. I've demonstrated this today. I will mention it tomorrow when we talk about the optimization of vectorization, but I will not revisit it. It was a long enough demonstration, and hopefully it made a good enough impression on you that you will look for these opportunities in your applications. So what next? In our diagram, vectorization and memory access. And if I don't know where to go next, I will ask the compiler. In the optimization report, the loop is vectorized, good news. But I have remarks about unaligned accesses, and also I have a remark about a peel loop. I will explain that alignment in more detail tomorrow. But today, let's address this peel loop. The peel loop has to appear because the compiler is trying to optimize the code for aligned data accesses. When we are starting to read this array from J0, ideally, we want it to start on a multiple of 32 bytes in the case of the Ivy Bridge architecture, or 64 bytes in the case of KNC and KNL. Why? That's because loading from memory is faster if you have this alignment on Ivy Bridge and on KNL. In the case of KNC, this is not a recommendation but a requirement. X of 0 must be on a 64 aligned boundary, 64 byte aligned boundary. If not, the code will actually crash. So to work around this architectural requirement, the code implements loop peeling. If x of 0 does not fall on a nicely aligned boundary, the compiler will perform a few iterations with a small math vector instruction so that it reaches an aligned boundary. So if this is my array, and these are aligned boundaries, and x0 is not actually aligned, the compiler will peel off the beginning of the loop and process it separately so that then it can go with nice big aligned loads. We can actually make sure that it happens, and we can drop the peel loop. And it involves two steps. Step 1 is changing the allocation. Instead of this malloc, I will do malloc. This is a different allocator that accepts two arguments. For the second argument, it accepts how many bytes I want it to align on. 1, 2, 3, 4, 5, 6. So now I guarantee that x of 0 starts the address of x of 0 is a multiple of 64 bytes. I forgot to say what alignment means. It means that the memory address is a multiple of 64 bytes. When we use this allocator, we also have to use the corresponding deallocator. And if we do that, we will have alignment at runtime. But at compile time, the compiler actually doesn't know about it. So we need to also use step 2. For step 2, I will insert pragma vector aligned. What this does is it tells the compiler to remove the peel loop because we know we can guarantee that it will not be needed at runtime. And indeed, after compilation, you will find that the peel loop is gone from the optimization report. And now this is a beautiful optimization report for this loop. No red flags, aligned access, music to my ears. Vector length 16, good. Normalization overhead. You know what? I said that normalization overhead being close to 1 is bad. No, it's not. I need to look up how to interpret this number. But the number that I know how to interpret is this one. It needs to be close to the vector length, and it is. Unmasked aligned unstride loads and nothing else. So this is clean, no other hints. Let's see if what we did helped. Okay, did we run? No, we didn't run. So the last step I did is malloc I replaced with malloc, and I inserted pragma vector aligned. Okay. And the last, again, I think I had a fluctuation. I know why this fluctuation happens. I didn't have time to go into that, but I will. This fluctuation on the CPU, sometimes I get lower performance values, happens because of the NUMA architecture plus no thread affinity. It is easy to fix. Maybe we should do that. But let me first get a clean performance measurement, then we will take care of these fluctuations. So this, yeah, now it makes more sense. So this is actually the performance, a good performance measurement, 434. $14.62. You can see that this is significant optimization 2150. Oh, I'm sorry, I promised 3 significant figures. I'm recording 4. Let's be consistent. Alright, so to prove to you that this was just a fluctuation and we can get rid of it, I'm going to hack into the makefile. And for the CPU code, I will change something. So instead of just running app CPU, I will do KMP affinity equal to compact. That's all I have to do. It pins threads to physical cores, prevents their migration, and it should get rid of these fluctuations. Rebuild. Rerun. And we will get the results in a second. Hopefully the same results, just they won't fluctuate. Yeah. Well, more or less. Okay, so we are where we are. The vectorization report is clean. And the last optimization area that we have not addressed yet, on the node level at least, is memory tuning. So where do we go with memory tuning? We can get some hints from the vectorization, from the optimization report. Let's see what it does. We already saw that this was clean. But if we look at the loop one level out, the compiler recommends loop interchange. Instead of ij, the compiler thinks it makes more sense to do ji. I think the reason why it recommends that is that the way that we wrote the program, this is a vector reduction. Well, CF is a scalar. We are using it in a vectorized loop, so all of these values will have to become vectors, and we will have to add 16 running sums and then add them together at the end. If the I loop was inside, it wouldn't be a problem. But if the I loop was inside, we would have a problem in that F would need to become an array, because F is the force on particle I, and I is now inside. So I don't want, this would cause problems with memory because we would have more data to traverse. So we will do that, but we will do it as a part of a memory optimization technique, which we will figure out from what I call the memory scalability test. The performance that we obtained was obtained with 16,000 particles. This is the default value. How about we change the number of particles and see what happens if we use more particles? So how about 65,000? Submitting to the queue. And what should we expect? I think we should expect better performance. We have this much data. We have this much computation. When n is increased by a factor of 4, memory traffic goes up by a factor of 4. But computation goes up by a factor of 16. So we have more computation relative to data movement, or so we hope, which means that data movement becomes less relevant. Well, let's see if this holds true. So this was for 16,000 particles. This last measurement. Now we are running a measurement for 65,000. And we are getting well, on the CPU the performance increased 516. On Knight's Corner 1260. And on Knight's Landing 2130. Sorry, so performance increased on the Xeon, but it dropped on Knight's Corner and slightly dropped on Knight's Landing. To get a better feel for what's happening, let's increase the problem size even more. So in the make file, I will quadruple the number of particles again. And rerun. Okay. I think now it's clear. So 510 gigaflops per second on the CPU, 940 on Knight's Corner, and 1650 on Knight's Landing. So Xeon Phi performance starts going down and down. Xeon is feeling good though. And this really illustrates the balancing act in Xeon Phi. It has less hardware to compensate for inefficiencies in your code. If your code is efficient, and it was efficient enough for small problems, then you get way better performance from the Xeon Phi than you do from a Xeon. But if your code is inefficient, well, then Xeon Phi is not the best platform until you optimize the code. So let's see what it takes to optimize this code. Why is performance going down with increasing problem size? The answer is once again in the innermost loop in the calculation. How much data do we traverse in this loop? We have 250,000 particles. For each particle, we read 3 quantities, x, y, and z. And for each quantity, we read 4 bytes. This is approximately 3 million bytes. Is it a little or is it a lot? It depends on what you compare against. Because this is data, it makes sense to compare it to the cache sizes. And the level 1 cache is 32 kilobytes per core. The level 2 cache is, well, depending on the architecture, but a good enough approximation is half a megabyte per core. There's also the last level cache, only on Xeon. It is of order, I think, for this model, 20 megabytes per core, megabytes per package, 12 cores. This explains why Xeon was feeling so well. The dataset that we are dealing with fits comfortably into the last level cache, but it spills out of the level 2 cache for Knight's Landing. Knight's Landing doesn't have LLC. It doesn't mean that Xeon is the winner for this code. It means that the code is inefficient. Because if we increase the problem size even more, and we have even more particles, they will spill out of the last level cache, and Xeon will suffer from the same performance degradation. So we should try to make the innermost loop short. There is a very well-defined way of doing that for this kind of calculations, and it is called loop tiling. There are two flavors of loop tiling, and I will explain them in session 10. But what will help us now is register blocking. See, the problem is this. We have some sort of a data set which is too large to fit in the cache. When we have I, j, and we're using v of j, we are reusing it m times. Because we have data reuse, it makes sense to do it while the data is still cached. Well, m times is this. It makes sense to reuse data while it's cached. But if we are not careful about the algorithm, we might run out of cache while we run the innermost loop. See, this is my B. I'm starting to read B, and red means cache miss, so I have to go to memory. This is a long latency operation. But I'm caching the last few elements, and I keep caching data of B until I run out of cache. Once I run out of cache, I will have to evict the least recently used elements, LRU. So by the time I finish this loop, I will only have the tail of B inside the cache, and the beginning will be gone. So when I come back to J0 and start reading this element once again, well, I am reusing it, but I'm reusing it so infrequently that I don't find it in the cache, and it's a red square again, cache miss. What I'm planning to do is I'm planning to rewrite these two loops as 3 loops. They will do the same operations, but in a different order. I will read one or a few values of B, or one vector in B, and I will reuse it several times for several values of I. Yellow means cache hit, free memory access. Then I will move to the next element in B, reuse it several times, and so on. The way to do this is strip mine and permute. I'm going to strip mine the outer loop in I. See, I'm writing it as II going from 0 to m with a stride, and then another one I to the next value of II. So step 1 is strip mine, and step 2 is permute, because see, originally I was here, and they moved it down there. Easier said than done if you have a real-world calculation. These two loops in I and J are not perfectly nested. If they were perfectly nested, the compiler might be able to do this optimization for us, but they're not. So we will have to do take some additional measures to make sure that the code is correct. What I will do is first strip mining. Take this loop, rewrite it as 2 nested loops. So where does it end? It ends, I think, here. Okay. Strip mining means I take this, and it goes now from in II from 0 to n particles with a certain stride. And then I now goes from II to II plus tile. I'm doing the same operations in the same order, so nothing has changed. What will have to change is I will have to move to permute the inner two loops. This will go inside, and this will go outside. Now you probably see what I meant when I said that we will permute the loops, but as a part of another optimization. So now we achieved two goals. We got rid of vector reduction, and we made the innermost loop short. How much data is used in this loop depends on the tuning value of tile, and I will declare it as 16 for lack of better knowledge. This is one vector. So how much data is used in this loop? 16 particles, 3 quantities, 4 bytes. This is 192 bytes. Enough to fit in the register file. So I'm not even reusing data in caches, I'm reusing data in registers. But just permuting the loops didn't make the code correct. F is the force on particle I, but I is now inside. So if I want to accumulate something, I have to move this outside, and I have to turn F into arrays. Because now I'm computing forces on 16 particles at once. This is how I reuse data. I have to initialize them. Remember array notation from session 3. This is array notation, an extension to the C++ language, supported by Intel compilers. Now this is good. Okay, initialize this. Here I'm computing the force on particle I minus II. And I actually have to finish the J loop before I do all of that. So this parenthesis goes up. And here, this is inside the loop in II, right? So this will also be a loop, but instead of a loop, it is more convenient to write array notation. So in array notation, the first element is start, the second element is count. I am operating on 16 particles at once, so I'm doing this. Hopefully not too mysterious what I did. I just made the inner loop short with the help of loop tiling. And again, I will revisit loop tiling in session 10. Oof, doesn't compile. It doesn't compile because I forgot II here. Okay, now it compiles. And let's see what performance looks like. Some calculations have finished. The CPU calculation is still running. It might take a while because we are solving a much bigger problem. Well, this is the latest performance results. The last three results are our numbers. So with tiling on the CPU, I'm getting 400, 1550, 2480. So that's all good, because look, this is better than ever. This is better than ever. This went down, and that's not good. This is where I have to admit that not all the time you can use the same exact code on all platforms. Sometimes you have to do some tuning, but usually the tuning is reduced to numerical tuning parameters. You don't have to rewrite code, you just have to choose different parameters for different platforms. And I've done this tuning, and if you look inside the solutions for instruction 4, you will find code that is fully optimized. And as you can see, what happens is for Xeon Phi, I choose the tile size 16. For the CPU, I choose a tile size of 8, which works better. Something else that I do is for Knight's Landing, I do loop unroll. I don't want to go into this right now, but I think what happens there is I just reduce the loop. I reduce the loop control overhead, possibly using more of the register file. But if you want to see how it works, go to Solutions Instruction 4, run the same exact command, and we will see the performance results in a second. So, platform-specific tuning. So, tune tile plus unroll. So, what we are going to see is the best performance result that I was able to achieve for this code on all of the platforms. And that result is 512 on the CPU, 1470 on Knight's Corner, and 3060 on Knight's Landing. This actually is just the effect of unrolling. And this is the effect of tile tuning. These are probably just fluctuations. So congratulations, looks like we have addressed all of the optimization areas for node level optimization, all of these 4. And I think we are close enough to the theoretical peak performance, and we have stable enough code that doesn't crumble when you increase the problem size. And I want to stop here. We don't have to really achieve the peak performance, and we cannot, because the peak performance is actually for the fused multiply add operation. And what we have in our code, we have some fused multiply adds, plus we have some additions not matched by subtractions, plus we have the reciprocal square root, which is as far as fused multiply add as possible. So what we are getting is, I consider it good enough. And if you want to scale past that limit, you really need to look into scaling across a cluster. We implemented MPI in a numerical integration code in session 5. We will have to be a little bit more creative with this n-body code, but we can do a simple enough MPI implementation if we allow for the assumption that the entire dataset fits in the memory of every CPU. So if every rank contains all particles, we can split the work done by different ranks and each rank will be responsible for moving only a quarter of the particles, so doing a quarter of the work. The trick is that after this calculation is done, we will have to propagate the results of rank 0 to all other ranks. We will have to propagate the results of rank 1 to all other ranks, rank 2 to all other ranks, and so on. Thankfully, MPI contains a collective communication primitive just for that, to synchronize pieces of a data set, of a larger data set that is scattered across multiple nodes. And that operation is called AllGather. I will now show you the MPI implementation. I will not try to do it live, but you can look it up in instruction 5. And it is quite simple. It uses the same principle as we used for the integral calculation. Start particle, end particle is the new limit for that main loop. And MPI itself appears at the end here when we call MPI AllGather 3 times, once for particle x, y, and z. So MPI does all the work regarding the algorithm that AllGather uses. And how well it works, we can actually see in practice. Let's just go to instruction 5, submit to the queue. I'm not sure if it's a fair enough comparison, but for your information, as we split the work between 4 compute nodes, we also increased the problem size by a factor of 4. So this is a weak scaling study. It will take a little bit of time to get the results out, but when they go out, we should have a good story to write home about. So MPI with 4 nodes using AllGather. So KNL results are ready. 12,180. Close enough to perfect scaling. And on the CPU, it will take a little longer to get the results, but they're coming. Still running, but I also hope to get a good enough speed up. Even though the CPU doesn't have access to OmniPath, each calculation step takes a lot of time compared to communication for this problem size, and we are fine. And regarding the problem size, you have to be honest with yourself. The greater the problem size, the better it will likely work. But for a smaller problem size, communication is more significant compared to computation. So what we saw is that with OmniPath, it still doesn't matter at this problem size. We have near perfect scalability. With Ethernet, scaling across 4 KNLs didn't work so well. We only get something like 75% efficiency. That is because communication actually takes a while. Looks like I didn't get a number for the CPU because it ran out of the allotted time in the queue. I can probably get at least some intermediate. 2060 if we use 3 significant figures. So again, close to a factor of 4, but this is for a large problem. What we covered today is a demonstration of all of the areas of optimization that we target in this course: scalar tuning, vectorization, multithreading, memory access, and communication. We have 4 sessions left in this course, and the plan is to address all of them in the next 4 days. We will not revisit communication again. We will focus on node-level communication, on node-level optimization. At any rate, thank you for joining us today. and I hope to see everyone again in the continuation of this course starting tomorrow. If you have any questions, type in the chat. Otherwise, goodbye.